uh, we're at this now part of Oracle. I'm Matt Abrams. I'm now VP of Engineering at Oracle, and we're part of a group called the Oracle Data Cloud. So this is a new group within Oracle. It's not the Oracle that you're likely thinking about when you think about databases and services. This is all about large-scale cloud operations, cloud data sets. Between the ODC, we operate on some of the biggest data sets in the world outside of the walled gardens that you're probably familiar with. And we're hiring like crazy. We have, I think, 12 open positions just on our group, and within the ODC, we have many more. So if you're interested in data science, in full stack engineering, in Hadoop and Spark and other distributed database systems, DevOps, React, and other front end systems, we'd love to talk to you. So come find me or come find Brad, or there's a couple of other Add This folks in the room. But we'd love to work with you. So if you're interested, please find us and we can tell you a little bit more about what we're doing. So thanks again for coming, and thanks to Craig for doing the pitch. So I'll hand it over to
Yep, and I've got some business cards over here if you need contact to reach out to. And with that, I'd like to introduce Craig. So there you go.
Thanks, everybody. Thanks for coming out. Let's see if we can switch this over. And share entire screen. All right. Excellent.
Your mic on?
Can you hear me? Is the mic on back there? Can you guys hear me okay?
Are you still muted?
Anybody back there? If you can hear me, raise your hand so you can hear it through. I can't tell if the mic's working. It sounds like it is.
All right.
No? No? It's not muted, but it may not be cranked up very loud.
Nope, yeah, it works.
All right, is that better? Can everybody hear me? Okay, I always feel like I'm yelling, but then people tell me I'm very quiet, so great. So that was a lot of people who raised their hands for knowing something about Jupyter and Pandas, and that's both. Nope, nobody can hear me back there? All right, let's see if I can put it somewhere where it's going to work better. All right, is that better? Okay, let's see if that works. Great. So as I was saying, both great and intimidating all at the same time, because nominally I'm a Java guy. But just recently I discovered that I don't like Java anymore. So I decided that now I'm going to be a Python guy. And so I decided that, yeah. So I decided everything I do, I'm going to do in Python now. And it kind of was good with the timing of our release of the open source version of React.ts. So I'm going to talk a bit about time series analysis. I'm going to talk about React.ts or time series database, but also to talk about some cool things you can do with the conjunction of the tools that hopefully will be interesting and useful for you. So it's going to look like, what is time series? I'm just going to do a brief, what is time series, just as a level set. What is React.ts? I'm going to talk a little bit more about that because I'm really excited about it, because we just open sourced it, which means you can go out and download it and use it right now. Some basics, like how do you create tables, how you populate with data, how do you query it. And then I'm going to get into some things like visualizing queries. And that's where I'm going to use Python, I'm going to use Jupyter Notebook, I'm going to use Pandas, because frankly, everybody in the world appears to know it already, except for a small minority of us. I'm relatively new to it. So boom, what does that mean? That means we're all going to be data scientists at the end of this presentation. How many data scientists in the room? This is better. Like last week I did a talk, like one person raised their hand. Apparently nobody wants to admit they're a data scientist. I got an art degree. I am not a data scientist, but I feel like it after having done this work. So time series wise, when we talk about time series, at least when I talk about it, I think about a high velocity stream of data that has a timestamp associated with it. And when you want to interact with that and do some analysis, you're typically going to ask a question like, what was the weather like in a specific zip code between March 1st and March 2nd or March 3rd, right? So some kind of range query that you're going to grab a bunch of data set and do some analysis on. So that could be some like patient vitals, tidal measurements. All of this really looks pretty much the same it's going to be at least mostly structured, if not fully structured data, and it's going to have a timestamp associated with it, right? So that's where React TS comes in. Now, if anybody here familiar with good old-fashioned Riak, the key value database? Okay, a few hands went up. So React KV is the key value database that we've been working on since 2008. It's a NoSQL unstructured data store designed to scale to massive size. You probably use it almost every day and don't even know you're interacting with it because not many people have even heard of us, right? But if you use any of the weather companies' products like Forecast on Demand on your phone or the Weather Underground, that data is coming from Riak. If you're a Comcast user and you've got Xfinity DVR, the data that tells them whether or not you're allowed to watch HBO, that's actually stored in Riak. So just a little aside, you may not have realized it, but you use Riak pretty often. Time series is actually built on the core of React KV. So what that means is it's a highly available database. It's made to be clustered. So there are customers who have clusters of 100+ nodes running in production, customers with over 500 nodes in the wild in production. Obviously that means scalable. Fault tolerant, if one node dies, it doesn't take your cluster down because it's completely masterless. Every node has the map of where all your data lives, so every node can serve every read or write. And operationally simple. If you have 500 nodes like some of our customers do, you really don't want to have 50 people managing that. We have customers with 500+ nodes that have 2 ops people responsible for maintaining that infrastructure. In one example, they wait until 10 or 12 nodes die before they replace them. And if you're running 500 nodes of anything, your nodes are going to die. Hard drives are going to fail. Hardware fails. They just simply sit back and wait for them to die in enough volume that it makes sense for them to go out and buy new hardware to replace it. So React TS is all of that, but it's slightly different in that it's optimized specifically for time series database, where the KV side of the house is designed for unstructured data. This is designed specifically for those time series like problems we talked about. Part of the way we do that, and we'll go into a little bit more detail, is data locality. But the other thing that's different is that it's not unstructured. It is actually very structured. It's going to look a lot like your standard relational table. In fact, you're actually going to create a table, and you're going to use a SQL DDL to do it. You're going to create columns. You're going to assign data types to those columns. You're going to determine whether or not those columns will allow null values. And then you're going to create primary key. This is going to look a little bit different than a relational database in how you do this because, number one, there's this quantum function. And a quantum function, what that does is it takes your timestamp, one of your timestamps in your table, and it says that's the value I'm going to partition my data on in my cluster on. And then you're going to set a range. Right here, that range is 30, and the units is days. So each partition of data is going to be a 30-day partition. So when I set up my partitions around my cluster for data, that's how it's going to be based on, what it's going to be based on. So that's the primary key, which is the partition key. The primary key portion, that's the local key. That's how the data is actually going to be physically stored on disk on each node where it's stored. That's how we determine how to collate it, how to sort it on disk. That allows us to do range queries across massive cluster sizes and then also individually at the local disk level. Sure, you can ask questions.
Quick question on that quantum.
Yeah.
That quantum timestamp 30 days seems like a bucketing function that you're using for the partitioning. Is that a fixed window or is it a sliding window in time, or how is it? What is it?
So that's going to make a little bit more sense in just a minute. I'm going to show you how that actually works. Okay. But it is a fixed window in so much as the first record gets written, then the next 30 days worth of records will go to that one partition. Once the date rolls over, they'll all go to the next partition in the cluster. Yes.
You could repeat the question for that, Mike.
Sorry, the question was, is that a fixed or floating window on the date? Hopefully that made sense, even though I didn't repeat the question. Thank you, Brad. So the big difference, we talked about KV. The way KV does partitioning of data is that it takes your key and it actually runs it through the SHA-1 algorithm, which gives you a number between 0 and 2 to the 160th power. We break that range of numbers up into partitions. In this simplified example, I have 32 partitions and 4 physical Riak nodes. And what we do is we hand out those partitions one by one until they're all spoken for. So that's how you know which node owns that specific bit of data. We also actually do replication, so we replicate each value 3 times, so you've got some high availability. But this is the basics of how we do it in KV. So what that looks like in practice, let's say here's our virtual nodes. Forget the individual physical server nodes, but these are the partitions. If the letter is A, it might hash out to that partition in there. If the letter's B, it might hash over there. Because of the SHA-1 algorithm, it's not going to actually hash out to consecutive numbers just because the letters are A, B, C, D. So you're essentially getting a nearly random distribution of data around your cluster, which is really useful for scaling out clusters easily and be able to plug in new nodes and not have to worry about where you're going to place your data or some of the sharding that you might have to do with other database products. You don't have to figure that out yourself. Now, with data co-location and the way we do that partition key in Riak TS, it's different. So let's say our partition is going to be 1 day's worth of data, and I write a key for the 1st of December 2015 and the 2nd. Notice that it's going sequentially through the partitions. Benefits are you can now do range queries. Another benefit, which might not seem intuitive immediately, is a speed increase. So even though TS is built on top of KV, it is significantly faster, especially in the write path. And there's a couple of reasons. One of them is the partition key. The other is some other optimizations we've done under the cover in the storage engine and the way we do writes to disk. In one example on a software cluster, 5 nodes, 16 gigs of RAM, 2 cores available to Riak KV, I was averaging about 25,000 writes per second using the YCSB Yahoo Cloud Service benchmark tool. Same kind of cluster size in a TS use case was getting over 135,000 writes per second with the same hardware utilization. Just to give you an idea of the kind of performance difference that you'd see in this. It's really designed for those high velocity time series type use cases, IoT, weather data, that kind of stuff. Really fast. I'm not going to in this talk because it would take up a lot of time, but we can certainly, we've got a white paper coming, and for people who are very interested, I have a informal paper I can give them that's been sanitized. But yeah. And again, because I work for Basho, I would always say, take my word for what it's worth for you personally and download it and try it with your own benchmarking tools and your own use case, because your mileage is going to vary, but depending on what you're doing with it. But I think you'll find the performance is pretty quick. And we'll see some examples here on a MacBook Air with 4 gigs of RAM, how ridiculously fast it is. But you got to try it yourself. Don't take my word for it. From quantum perspective, if you're going to do time range, we have to give you options. So there's days, hours, minutes, seconds, and you can specify the number of those that you're going to do. In some testing we did with a weather-based use case, we set up the quantum for 15 minutes, and we were storing 1 billion individual records per quantum. So that's 1 billion records per 15 minutes. Just to give you an idea of kind of what that looked like. And that was on a cluster sustaining 1.3 million writes per second over like a day of writing. Data types are supported right now: varchar, doubles, signed 64-bit integer, booleans, and timestamps. And the one thing I'll point out is that we do timestamps a little bit differently. They're Unix epoch. So milliseconds since the epoch. It's an actual number, not a timestamp, and that is really helpful because it's more efficient and easier to sort on, and you don't have to do a lot of conversion with it. That's going to come into play here in a bit. We also give you SQL, actual SQL to query on. So for those of you who know SQL already, that's very handy. This is the kind of query you're going to see commonly. And we mentioned the epoch. So what you're seeing right here is actual epoch written out. If you query using SQL, you do have to convert your time date format into the epoch, which fortunately modern computers make very easy to do. So, and I'll show some examples in code that I'm going to show. For equality, we have all the equality operators supported, pretty common. And then we've got aggregates. So right now, these are the aggregates that we support in version 1.3. We have 2 standard deviation because apparently people like 2 different ways of doing it commonly. There is the sample and the population method, so we support those. And actually, by the end of the year, we hope to have the ability for you to write your own functions. So right now, that is not supported. The underlying code is there. We just have to add it and test it, and by the end of the year, hopefully, you'll be able to write your own. So if those standard deviations don't do it for you by the end, the end of the year, hopefully, you'll be able to write your own. All right. Now, if you're going to interact with it, we've got 2 APIs. There's a protocol buffers API and an HTTP RESTful API. If you don't want to go directly to React TS, we already have these clients released. So our engineering team has written Java, .NET, Ruby, Python, Node, Erlang, and PHP clients already. I'm going to show you the Python client in a bit, but there are options. All right, and Spark. Spark users out here? How many Spark people? All right, so you can query and you can load this up in an RDD in Spark, which is super handy. So if what we give you right now in querying doesn't give you all of the horsepower you want for things like machine learning, you can load your data into Spark directly, and it's quite fast. So not an afterthought. This was something we built in up front. That's important. All right, so I want you to go get React TS if you're at all interested in time series. I want you to try it. I'm going to hopefully show you in the next little bit how easy it is to get started. But if you want, that is the direct location to go to the home page for the documents and the downloads for React TS. I'm going to whip over to that right now. So this is the Basho Docs homepage at docs.basho.com. You can see we have a couple other things out there like Riak KV, our cloud storage solution, but we're looking at TS specifically. And if you go there, there are downloads. You can also find links here to the source code on Git if you're really interested in seeing the source code as well. But these will give you your favorite distributions for Debian, Mac OS, RHEL, CentOS, Ubuntu. And if you don't see yours, you can roll your own, build your own version. Not Windows, unfortunately, sorry. Also pretty good docs. So from there, I picked Python because, as I mentioned, I've sort of gotten really tired of doing Java. I've been doing it for a long time, and I realized Java is interesting. So honestly, you know, like if you just said, build me X, Y, or Z, I would probably start coding in Java because I've been doing it so long, I think in Java. But I realized that at a certain point, I have to break out of that mold and try something new. And all the cool kids tell me that Python and data science sort of go hand in hand. So one of the things you want is the Python client. And if you are using Python already, it's really easy. If you have pip, you just say pip install Riak. That'll grab the latest Python client, and you're good to go. Super easy. I also picked Jupyter Notebook because I know a guy who showed me some stuff in Jupyter Notebook, and I was like, that's really cool. And I'm going to use that for demos. So I downloaded Jupyter Notebook a few weeks back, and I've been doing lots of stuff on that. And then he also said, there's this thing called Pandas. And I'm like, yeah, I know, I've seen them at the National Zoo. And he's like, no, it's a data science library. It does lots of stuff for you, so you don't have to be a data. And I was like, okay, I'll check it out. DC joke, right? Outside of DC, I don't know how many people get that one. All right. So how many people use Pandas already? Okay, fair number. But for those of you who don't, it's an open source library that just comes with a ton of data sciencey things built in, including features that allow you to grab files from disk, rip them into Pandas to do analysis on them, and write files back out. It's amazing how easy it makes this stuff, and you'll see a lot of that here in a bit. Also, I'll let you know that all of the code and this slide deck are available on Git in the spirit of open source. So if you are interested in trying any of what you see, you can go grab it. There's a bit.ly link here, but if you don't want to remember it, you can just check right from like GitHub, and fortunately it shows up. You can see it right there. It's right there. That's the whole code that we're going to see here. Okay. So for those of, how many people use Jupyter Notebook already? It's always good. Last week up in New York City, I was doing a thing, and like there were 80 people there, and I think 70 of them already knew more about all this than I did. So it's kind of fun. Basically what it allows you to do is it allows you to load code up into the web browser and execute it. So I'm going to show you step by step some of the stuff you can do. The first step, of course, is we've got React TS installed on the machine. I did nuke my React TS instance, and I forgot to restart it. So I'm going to actually go in. All I did on the Mac OS was grab the compressed contents from the website, unzip it into a directory, and now I'm just going to say React start. I didn't do any tweaking to the config files because I'm just running a single instance on my machine. So I just said React start. It's starting up a React node. React is started. If you want to make sure it's started, you can say React ping. It'll say Pong. You can also ask what version am I running, and it's 1.3.0. That's the open source release, so we know we're on the right version, which is useful if you run more than one version of React on your machine like I tend to. Okay, so with that said, I can now actually move forward. So inside my web browser, I've got a bunch of Python code that I've already written, tested, and make sure it actually works, so I didn't just stand up here while it bailed on me. I'm importing the React client, and I'm connecting to it.
Can you make that a little bigger?
I can, through the wonders of Chrome wizardry. Is that better? A little bit more? Okay. Is that excellent? All right. Okay, I can even read it now. Okay, so I'm going to be creating a table called water meter data. So that first block, all I'm doing is importing the client, setting it up, setting that variable. I hit play, it runs that code. So now it moves me automatically to the next block, and here's where I'm creating that SQL query, that DDL that I showed you before. It's exactly the same as what I showed you before. I changed the number of days, and I can explain that in a little bit. But then I added this little block down here at the bottom. I realized, I think I mentioned before that we replicate data by default 3 times in Riak for high availability. But because I'm only running a single node on this little woefully inadequate MacBook Air, I realized that replicating my data 3 times was probably pointless. So the nval equals 1 is saying that when I write data to this table, I'm only going to write data 1 time. I'm not going to replicate it 3 times.
Can you update that after creation?
Not yet. So currently in 1.3, once you create a table, you cannot change the table or delete the table. You have to, that's coming. We have drop and alter coming, but right now, and it's a very complex architectural discussion about how Riak works underneath the cover, but you can't actually change a table once you create it currently.
Is there a trade-off, or have you done a trade-off analysis on specificity for timestamp when you're doing the quantum? So based on the volume of data and how quickly it's coming in?
It's a great question. What's the trade-off on the specification of the quantum? So a couple of things. Think about how we do distribution of data around your cluster. You want to utilize all of your machines equally in terms of storage, but also in terms of the ability to handle queries, reads or writes. So the more evenly that's distributed, the more horsepower you're going to get out of your cluster altogether. Now, the flip side is the more quantums that you have, the more distribution, then you're going to suffer a little bit on the query side, right? It'll take a little bit longer for that same query to complete. The other thing I'd point out is that there's a limiter in the query engine. It's configurable, but by default, you can only query across 5 quantum. And the reason is these clusters can get quite large, and the data sets can be very massive, and we don't want you to ask for all of the things. That's Right, that's the reason. But you can go in and you can change that for if your use case, if your data set's not that big, you can change that. But that's part of the reason why I set the quantum here in this use case to 80, because it's going to suit the queries I'm going to do, and I'll make sure I have plenty of room to cover the time span I want to query.
Does that include for 5? Does that include just a straight out data? I mean, obviously for a data frame where you're returning every single row out of the set versus aggregation.
It's any query. You would have to adjust the quantum limitation on your node. So, or do multiple queries.
Will you know if the data, if you made a query that was over more than the limit of quantums, or will it just return a subset of the total data?
So the question is, will you know if you ask for more than what you're allowed to ask for? And the error message that comes back will tell you that you can't do that. Please try again. With
so
a,
it won't give you a wrong answer. It will give you an error.
correct. It will give you an error message telling you you've exceeded the number of quantum. So it's helpful that way.
Sounds like a good feature ought to be if you tell it how much data you expect to have, and then let it figure out how many quantum you should have. Since you have a best practice and you have these rules.
The statement was, it sounds like a good feature would be to have a calculator basically to tell you how many quantums. And I actually agree with
Or to
that.
specify the number of records.
Yep.
Have it computed passively.
So the one thing I'll tell you is almost everything you do with React TS is going to be really easy to do. The hardest part about React TS is figuring out the appropriate way to model your partitions at that point. That's really the hardest part. Once you figure out roughly your use case and do some testing on what that looks like performance-wise, and you set your quantums that are going to fit both your write and your query patterns, everything else is remarkably easy. But it's kind of the traditional data modeling process, right? The modeling of the data tends to be the hardest part, just figuring out how you're going to actually store data as opposed to how you're going to query it. Because once you've figured out, some of your query patterns in advance, then you can figure out how you're going to model it. This is where all your energy goes. It's not in the ops, it's not in the querying side, really. It's right there. And it's not that hard once you get used to it. But I'm going to run this. And it's okay, it's done. It'll tell you it's busy up there, and you can see that the response back is the water meter data has been created successfully. If I run this again, I'll get another response. That came back much quicker. It's telling me it's already created. It can't recreate it. That's pretty clear, right? And then I can run describe. And if I run describe, it's just going to bring back a list of all the columns and data around that. Now, the other really handy thing that we have, which is kind of fun to play with, is the React shell is basically a REPL for React TS. Everybody know what a REPL is? Okay, not everybody. There's only. So it's an interactive command line that allows you to issue commands against a programming language or a database. So in this case, it allows you to do SQL against React TS. So I'm going to say describe water meter data. Don't forget the semicolon, and it'll output that. And that's basically the same exact information, but in a prettier format. Tells me my table has been created and what the specifications are for that table.
There's no reference to quantum.
I will make, yes, that has also got the same issue as the browser. I will. How's that? Oh, awesome. Yes, it does not actually tell you. This is one limitation that I've already mentioned to product that we should really put the quantum in here. It doesn't tell you what the quantum is. So, all right. So now that we've created the table, we can go back to, let's get rid of this. Let's write some data. So I'm going to create a fake data set. I wasn't clever enough to go find a really interesting data set in advance, so I just faked up some data around water meters. Again, I'm going to import the React client, but I'm also going to bring in the date-time library and some time delta stuff because I'm going to do some time deltas as I go out. I've got my water meter data. I created a function here, and this could be handy for some of you if you start to play with it. It's very basic, but it's actually just going to take a list of lists and write that list of lists to React TS. So React TS can take a batch of records And those records are just a simple list of lists, an array of arrays if you're not using Python verbs. But essentially, each row of data as an array and an array of those rows of data. And it's going to write that and tell us whether or not it's written it successfully. I've also got some starting values for my data. And I'm going to run that just so I've got that code handy and ready to execute. And then this while loop is going to go through and it's going to generate a year's worth of water meter data. And it's just going to go through and do some variations on it. So when I talked about the array or the list of data, this is the first starting record with those values. Everybody see that? And so what I'm going to do is I'm actually going to generate 100 of those. And then I'm going to write that 100 to the database. And then I'm going to do the next 100 because you can batch things to TS. It's more efficient than looping through and writing each record individually. So that's 100 is probably about the ideal batch size for Python and the Python client. So if you're going to do this, 100 is probably a good batch size. All right, this is actually going to take a little bit of time. This is where Jupyter is not great. It is not as efficient as doing this from Eclipse. When I execute this code in Eclipse, it takes about 3 seconds to generate the 8,000 records. It takes a little bit more than 3 seconds in Jupyter. Okay, it's done. Or at least it said it was done. It lied. It's much quicker in Eclipse than it is in Jupyter. This is where the browser isn't nearly as efficient. All right, okay. So we've got 8,500 some records. 7,000, sorry, 8785, okay. So, and you can see I output the records so you could see the format of the records that was coming out. On the Python side, when you write dates, you can actually write the Python date format to Riak TS, and the client will automatically convert it to the Unix epoch for you. That comes in handy. And then we can do some simple queries based on that. If anybody have questions about writing the data, again, all this code's available. So I'm going to run that bit of code that brings in the Riak client again on this simple query page. The one thing you'll notice is I changed this here in the Riak client. I actually pass transport options and convert timestamp. That's because coming back from TS, it passes the Unix epoch back to you. But later on, if you want to do some stuff in Pandas, for example, some time series analysis, you'll probably want the timestamp format. So this will pass back the Python date instead of the epoch. So that's handy bit of information to use that. Okay. All right, so there's a couple of ways that you can query it. The first way is if you want to actually get one individual record, you can do that in TS without having to use SQL. This only works for individual records. Most of your queries against TS are going to use SQL. But in this case, what you do is you create a key. And in this case, the key I'm looking for is that date, the customer ID, and the meter ID. And if we go back to look at the create table statement, let me just pull it back up on the slide where it's easy to read. Yeah, sorry. Harder to do when it's already in slide mode. So the partition key just exists of the time. It's just the time, right? But the local key is timestamp, customer ID, and meter ID. The reason for that is we want to make sure that we have a unique key locally, right? So you can send a lot of records to the same partition that have the exact same timestamp, but if they don't have some kind of additional information associated with them, you'll just overwrite the first record if it's just timestamp, right? If you send 10 records with the same timestamp, Riak TS is only going to store 1. So we add customer and meter ID here so that we have some differentiation and make it a multi-part primary key for the local key. That way you can have more complicated unique IDs so you're not overwriting your data constantly. Does that make sense?
Do you know if you've overwritten? Or?
No, Riak TS does not know or care. So Just so you know, it's when you write your data, it's just going to overwrite your data. So you need to make sure that you've got enough in your primary key to ensure at a local level, you're going to have uniqueness. So all writes are essentially upserts. The way it works is that Riak itself, Riak, KV, and TS are append-only data stores. So when you write a record as an update, it automatically is a deletion of the old one. Now, in KV, it's a little bit more complicated than that, but in TS, it's just update and move on. Yes. Okay. So in that case, you can't just ask for the timestamp because the local key is actually that 3-part key. So I have to pass in the 3-part values. I use the client and do a TS get, passing in the table name and the key. And I did not clear these cells from the last time I run it, but you'll see what comes back. That's our record. So the next step is to do a query with SQL. And in this case, you'll notice I'm only passing in a range of dates. So I've got my dates, my start date, and my end date set up. And I'm actually doing a little bit of calendar work here to convert it into the Unix epoch so that when I write the string, it's the actual number and not the date format. But I'm only looking for things between those two timestamp values. I don't have to add the customer or the meter to that query. It's going to pull back all of the data. It's not going to filter based on customer or meter. Now, I could add that to the query. I don't have to do it that way. I could add filters on it if I wanted to. So run that. I output my SQL so you can see what it looks like, and then the records that get returned. It's also nice because, again, you could do this in the shell. I saved a smaller query with fewer records, but I could go back into Riak shell, put in that query, and Riak will nicely format it and print it out so I can see my data. Obviously, those values are doubles, so it's not limiting the precision on there very much. No, these are the actual individual rows, the data. Yeah, that's coming back. All right. So this next example here actually shows if I add a filter, it's just a simple filter. Some of these records have fault conditions, so I want to pull back errors on and see what kind of errors people are having. So that they're having power outages, so data is not coming back at a certain point on their water meters. Okay. So with that said, the other stuff you can then do is aggregations. And you'll notice with aggregations, maybe I want to generate billing information for water meters. So I'm taking the max of the total gallons, subtracting out the minimum total gallons. I got the average water pressure, average gallons per hour. I'm doing that for a specific meter for a specific time period. And so it's telling me that they've used 4,998 gallons. It tells me what the average water pressure is going through their system and the average gallons per hour that they're using during that time period. Just to give you some ideas of how you can simply query and get that data back. Questions about simple queries?
Can you do sort by?
So not yet. You can't currently do sort by or order by in TS. Right now, they're adding that in, and we are looking at hopefully getting that in for 1.4 or 1.5. I'm hoping 1.4. So hopefully the next release will have order by, sort by, possibly group by.
So the default order is the sequence of the.
Yes. The default order currently is the kind of sequence of the primary key. Correct.
I believe the primary key is basically the compound key.
The local key, yes, can be a compound key. It doesn't have to be.
So how many elements can you specify?
I'm not sure that there's a limit.
But
The minimum is 1.
one, but the more you add,
Yes.
You're going to have, index space.
When you pick the number of elements for that local key, you have to keep in mind what is your query pattern and what is the minimum number you need to achieve uniqueness, right? So in this use case with the water meters, the way I thought about it is you could have customers that have many locations and thus many water meters, but one bill. So you would need to have customer and meter as part of the primary key to ensure uniqueness, right? You couldn't just do one part of that.
So is there any way I can add a secondary key or any other?
Not currently, no. Right now, the keys.
According to the performance, instead of using one key, you could have more than two more keys. So that depending on what query I'm running,
Mhm.
you see what I'm saying?
We're talking about indexing versus
Yeah, so right now, all of the indexing is key-based. You can't add additional separate indexes on the data. No. Maybe in the future. On the KV side, we have solar indexing. So maybe in the future, we will also do solar indexing of your columns and rows of data here. It's something we're looking at. Part of the issue with that is the data is written in a very different format in TS, so it's not currently a format that we can transition directly over to solar.
And what about joins?
The question is, what about joins? Joins are not currently supported, but they are in the works. We are working on engineering links, key relationships, which is pretty cool for a NoSQL database. All right, so I'll just show you really quick. One of the common things that people ask for is downsampling. A lot of people have taken to calling it downsampling. I'm not really sure why. I don't think that's a scientific term. I consider it more roll-ups, taking data and doing roll-ups. We don't have that built in, but it's really easy to do using basic SQL querying. So in this example, I've taken that data set we just created, and I'm going to create a monthly roll-up table. So, if you've got water meters, you're billing someone for their utilization of the water. And every time that person goes to the website to see their bill, you don't want to regenerate that data or regenerate the roll-up for all the water they've used in the X number of years. So why not create a roll-up table? And I've done that here. I've actually set my range of days to 3,000. That just ensures that I've got like 15,000 days that I can query across if I'm interested in doing that. So I'm going to execute that. I also added the end val equals 1 again. My table's been created. I can verify that by hitting describe and seeing that information. And then what I'm going to do is I'm going to write the rollup. And here I actually just created a quick function that does that conversion to the epic. So that's another thing. If you don't know how to do it, you can steal that really quick. It's not beautiful code, but it definitely does what you want it to do. And I'm going to loop over the year's worth of data, and I'm going to create essentially 12 records, which are just rollups. And that's what the records look like. They've been written, and then you can verify that by running this block of code and return them. Okay. So that's where we get into being able to do a few more interesting things with Pandas. So we've talked about this before. At this point, you can do basic SQL, get data back, do some sum and aggregate type of things and figure out some things for yourself. But if you want to go beyond that really basic ability to analyze your data, this is where you might want to look at the Pandas library. I highly recommend it because you can look very clever in a very short amount of time without actually having to know how to do a lot of stuff. So I'm going to import Pandas, the Riak client. I'm still using that transport option to change the date into an actual date format because that's very handy for what we're going to do. Pandas does not know how to deal with the Unix epic. I've got that function there. These are just a couple of the functions that I've got created. Now, one thing I'll tell you is what comes back from React TS when you query it isn't really a list of lists. It's a time series object, and there's some additional bits of data attached to that. When we work with Pandas, we're going to create a thing called a data frame. Those data frames can be created from all kinds of different data objects, but not a time series object at this point. So I've got this really ugly little function here that takes my data, my time series object, and turns it into a list of lists, an array of arrays, so that we can load it into Pandas. All right, so now I'm going to do a query, kind of the same query we just did before. That returns the time series object, and I'm going to take that time series object, and I'm going to run it through this TS object to list of lists into my boring list. It's boring because it stripped out all the interesting data that the time series database returns. And then I'm going to load that into a data frame here with Pandas, okay? The next thing I'm going to do is we've got columns, and so I'm going to give them names because we want to be able to look at what the names are of those columns. And I'm also going to set the index of that, and you'll see what the index is in just a minute if you don't know. All right, so I've done that, and when I call df, what I now see is, thanks to the magic of Pandas, it's actually going to output a nice, neat, formatted table with all of the data that I just queried. It's got the columns. This is my index, which I indexed on my date. And so you can see already that Pandas has provided a little bit of value.
Can I ask you a question? So the original water meter data, I mean, that you created or whatever, but if we had real water meter data in a text file or something, we could have just read that right in the Pandas.
Absolutely. So you could take, Pandas has the ability to read in a large variety of formats, including CSV, very handily.
So why do we need Riak?
So the reason so how big of a data file are you going to load up? So on this single machine here, and even on my MacBook Pro with 16 gigs of RAM, I could maybe get through a 200 meg file on that without completely grounding to a halt. And then what would I do with all that data? So if you're actually one of our customers for KV is actually a metered company in the UK, they take billions of readings a year. And that's why you would use TS. You wouldn't, if you have a small data set, like someone gives you a 50 meg file and says, tell me what's in that 50 meg file, you could load that right into Pandas. Yeah. But, if you've got billions of data points, you're not going to load that directly into Pandas. You're going to query it, get some subset, and that's why you use TS. You use that to store all of the data as opposed to a subset. Good question. So now that we've got the data frame, we can do all kinds of cool things with it. In this case, I just say df, and I specify the gallons column, and it just shows me that column. So if you don't want to see all the columns, you can go through and limit what you're seeing. The next one here, I take my data. Oh, so one thing, I got to start killing stuff off. When you run all these Panica, you start using up all the memory on your machine and everything starts getting slow. I put in a list, a range of dates here, and then it's only giving me a slice back of the data. So if you had that really large set of data, but you only wanted to look at data in a certain time frame, you just tell your data frame, only show me the records between those 2 dates, and it'll give me a slice. So that's some of the stuff that's built in. You can query and say, what's my index? It shows you what the index fields are, what the column fields are. Some other cool features. There's a lot of cool features. I'm not going to go through them all because that would be time consuming. But if you do a describe on your data set, it'll come back with the numeric fields, and it will give you, obviously, count, which is there's only 12 records, so you're going to get 12 values. But it's going to give you mean, standard deviation, and min through max values. So that right there also gives you some really basic, quick value from actually using this tool to quickly kind of see what you've got in your data set, compare the values, and be able to come to some conclusions about your data. Beyond that, cool things like sorting the data. And if you're into pretty pictures, you can use matplotlib. And just in those 3 lines of code here, I'll take that data frame that I've added, and I'll be able to generate a graph from it. So lots of people go out and get things like Grafana and that to do visualization, but really quickly with a little bit of Python and a little bit of Pandas and a little bit of Jupyter, you can start visualizing your data and use this for things like basic system metrics and that. If you're just, it's coming. Not yet. We're working on it. We are working on it. That is a common request. So in the future, we will have a Grafana plugin for React TS. But in the meantime, you can really quickly do a lot of the same stuff with Pandas. The one other thing I'd point out is if you're into those graph things, those tools are really pretty advanced. I won't go into all the options, but I pulled back a small subset of the data, and you can just see columns of data for gallons, and I'm going to do some different visualizations. So you can go in, change the graph size, change what the labels are, change the units that it's being measured on. So these are very simple. There's chapters about how you can create really pretty graphs with Pandas that aren't quite Grafana quality, but they're pretty good for free, right? Yeah, well, it's all kind of, all of this stuff is free and easily downloadable.
Why are we software developers?
I don't know how we explain to our moms what we do for a living. All right, so with that said, let's see here. Now I got to go through all these slides because I went all the way backwards. That's really a quick down and dirty. That's how easy it is to get started. The code is there. You know, if you use it, great. If you find something you don't like about it, submit a pull request. I'll change it. I don't care. I don't really care. If someone finds a better way to do it, wants to write a better version of any of those functions, I really spent very little time writing those, and I'm not a Python guru, so I know already that I have a Python, another Python example out there that shows you all of the things you can do with React TS using the Python client. And one of the guys on our ProServe team came along and said, that's just not elegant Python. And he rewrote the entire thing. And I just merged all of his PRs back into mine because I was like, hey, you're a Python guy. You know what you're doing better than I do. It all seems to work, so I'll take it. So if you have any PRs, I'll take them. Issues, any of those, I'll take them. But if you're going to try it out, just, you know, feel free to shoot me any questions that you might have. Oh, I guess there's my email and my Twitter handle. But any other questions that you might have?
It seems to me, we kind of touched on this a little maybe, that Elasticsearch would be a natural competitor to React TS. Can you draw a distinction and so forth?
So the question is really, is Elasticsearch a natural competitor? And I think Elasticsearch is kind of a natural competitor to like everything in the world at this point. That doesn't mean it's the right choice. So Elasticsearch is really good at indexing JSON documents. So if everything you have is a JSON document, or you want to make everything a JSON document, you can do some stuff with it, and it does pretty good at certain things, but at a certain point, scaling-wise and ease of operations, you're going to lose it. We're going to be easier.
Semantically, it's kind of equivalent. It talks a lot about time. Time is a very important thing. And indexing, there's all kinds of neat things you can do to join different indexes and partitions together. But you're saying that eventually you're going to be better at a larger enterprise scale than Elasticsearch.
Well, and there are certain areas that we excel at, like the distribution of data and the speed of writing, where I think that we would be superior, and also probably in terms of footprint. So what we find, we don't really look at Elasticsearch in the competitive space. We tend to look more at Cassandra. Cassandra on all fronts tends to be our main competitor. And So when we built TS, we had the nice ability to look at what Cassandra had done as far as the time series side and hopefully do it better. And we found through our comparative testing that we are faster and we have a smaller footprint, smaller number of nodes. So comparing it to Elasticsearch, I don't know, because we probably wouldn't. We don't, although they are very well entrenched in things like log file analysis, it's a little bit of a different kind of use case than what we're really targeting most of the time.
Did add this kind of switch from Cassandra to Riak, or using both?
No, Addis still is a heavy Cassandra.
Yeah.
How you're mentioning.
Oh, React is the
React.
Yeah.
React.
I know. Sorry, I talk kind of fast sometimes, and that.
That's what first I used.
But that's a great idea. We could talk to them about that while we're here.
Did you have a question?
No, I was going to try to think of a witty remark to come in.
So could you go back to the slide about co-location?
Which,
It was your first or second one. No, further back page. Yeah, so actually the one before that with your example with A, B, and C.
yep.
So could you just explain that a little bit more for someone who doesn't know a ton about databases? So are these characters that are being saved in specific partitions?
So in this example, sorry, in the KV world, we have buckets. Or in the TS world, the bucket is a table. They're actually the same thing, right? A table gets mapped to a bucket on the KV side. But so letters is the bucket, and the key would be the letter D. So when we run D through this SHA-1 algorithm, it spits back a number. And maybe that number's 2. But then if we put E into the algorithm, we might get 5,392. So just because the letters are next to each other in the alphabet doesn't mean they'll be next to each other when we hash them. So it's not completely random. It's an even distribution, but to you, looking at where the things end up in the database, it'll look random.
So random key.
Random E, yes.
And E.
So that's to protect against data sets that might be skewed one way or another, and therefore will land in one partition, but not to be heavy use in one partition.
Correct. So that
Correct.
even the consistent hashing of keys in Riak KV is designed to keep you from having hotspots in the storage of your data in a cluster.
Let's get 2 more questions. And,
I've been blurring my eyes on the quantum stuff.
Uh-huh.
The sharding, I don't understand. We said quantum 30D. Is that one value for 30 days? 30 values? What does it mean?
So when you set up a quantum, and that quantum, let's say it's 30-day quantum, that means every record being written that has that key pattern that's within a 30-day range will go to that one partition. It could be 1 billion records, it could be 10. Yes. And then when when that time period rolls over, then it moves to the next partition.
If you're writing your data sequentially on time, you're not just running a year's worth of data. Are you hammering the same partition?
Initially, yeah. So initially, when you start writing data, data is going to be going to, if it's all in that sequential time frame, it's all going to be getting written to the same partition.
I guess I'm just imagining. Let's say I create that table now. It's daily quantum.
Mm-hmm.
So I'm writing my daily quantum. And it's today.
Mm-hmm.
So every record I write today is going to go to the same partition, and then tomorrow every record it's going to go to
For a
another
given
partition.
key.
For a given
Yes.
for the rest of the key.
That's correct. It depends on what else you've put in the partition key. It's possible you could actually have additional components to the partition key.
Compound partition
Yeah.
will prevent that.
Yeah. You had a question, Michael?
What level of consistency do you expect?
This is eventual consistency, but when you think about it, this is kind of a write once database, and this type of data isn't typically something where a microsecond later you want to query it. There probably are some use cases like that, but it's less common because this is store tons of data and then do analysis on the data. But it is eventually consistent because remember there's replication. So every time we write it, although in the examples I showed, I changed the end val to 1. But if you have the normal end val of 3 and you're writing on a real cluster, it's writing to 3 different nodes. That's not happening at exactly the same time. So your read may not return what you expect it to.
If you have any additional questions, Craig will be here for a little bit longer. But anyways, I'd like to thank Craig and Basho for and of course add this and Oracle for providing location, hosting, and drinks. If you thank you. If you have any additional topics that you guys would like to hear, please let me know. You can either come talk to me now, or just message me on Meetup. Also, my email I think is in the messages I send out. So please feel free to reach out to me. Or if you'd like to talk, have a topic, please definitely come talk to me. So I look forward to seeing you guys sometime soon for the next meetup. Thanks.